So in the previous lectures, we developed basic mathematical tools which will allow us eventually to write down the field equations for gravitation that Einstein wrote down in 1916. And so the basic ingredients that we looked at over the course of the last few lectures was, first of all, the metric, right? The metric is a fundamental quantity because it allows us to determine distances between space-time points, right? And it is also related to the Newtonian gravitational field, right? This fundamental relationship that connects the G0 right, to the Newtonian field. We also learned about tensors. We understood how you would write things down that would be form invariant, objects that would transform in a simple way under general coordinate transformation, which would allow us to write equations which are valid in any coordinate system. And so we learned that out of the metric, we can construct the affine connection, which is not a tensor, but then out of the affine connection, by taking suitable derivatives, we can define this Riemann tensor, which is a genuine general coordinate tensor. And we also saw how by contraction, we could construct other quantities like the Ricci tensor and the scalar curvature. So we have at our disposal at this stage, right, all the basic mathematical tools that allow us to proceed in a more physical direction in trying to write down an equation that is suitable for describing relativistic gravity, right? So that means that we are going to first write down the things that we know about. So one of the things that we learned is that G0 is equal to minus 1 plus 2 phi. And this applies to the weak field limit. Right? And we also, remember, looked at Poisson's equation, so that we have that the Laplacian of this field phi is equal to 4 pi g times rho. So we know that the Newtonian field is related to the distribution of matter. Right? So matter enters in here, right? And we also know that we have, in general, this is something that we discussed in the first lecture, the matter is described by an energy momentum tensor, right? And that energy momentum tensor we wrote as T alpha beta. And we do know that the T0 is essentially the density, right? So we have a relationship on the one hand between at least one component of the gravitational field in the relativistic theory and the Newtonian field. And on the other hand, we have a relationship between what is another tensor, the energy momentum tensor. One component is the rho, right? So that means that we can, first of all, rewrite what we have learned so far in a form that involves just the not components, right? So we can write that the Laplacian of G0 is equal to minus 8 pi g times the T0, right? So that follows from the things we have learned so far. And so if this equation is supposed to be invariant, then it has to be promoted to something that, instead of having just not indices, has to have all indices present, right? So that means that we are going to write this as G alpha beta, right, is equal to minus 8 pi g times T alpha beta. So promoted to an equation of this type, which at first would hold just in an inertial coordinate system, where the T alpha beta is the special relativity tensor that you would get by promoting the T0. And the G alpha beta is an object that at this point we don't know what it is going to be, except that it is two-indexed, right? And it has to appear in this way. So this is to be determined. Right, this object is to be determined. And we can, again, promote this to a general covariant form. Right? A general covariant form will now use the T mu nu. So it will be something that will look like G mu nu is equal to minus 8 pi g times T mu nu. Right? where incidentally we should not confuse this G with the G mu nu, because the capital G mu nu is some tensor that needs to be determined, and the G, of course, is Newton's constant, right? So this is some tensor that needs to be determined, right? And so there is a big question mark under that G mu nu, and now we're going to write down all the properties that that G mu nu needs to satisfy. Right? So what is it? So we write down the properties. Of the G mu nu, right? And well, the first property that we are going to list is the fact that G mu nu is a tensor. Is a tensor, so that the equation of form invariant, right? Remember, on the right-hand side, we don't have to really think much about this object because we know what it is. We know, we already discussed what the energy momentum tensor will look like in a number of instances. So for example, if you have n particles, right, it's a sum over n pieces, each one of which represents the kinetic energy, for example, associated with each particle. If we have a perfect fluid, then the T mu nu is the T mu nu for a perfect fluid. So the right-hand side is well understood at this stage, right? It's the left-hand side that we have to work on. So we know it is a tensor. Also, we will assume that it is G mu nu is made out of derivatives of the metric, right? And in fact, we're going to talk about first and second derivative of the metric. So it will contain things like dg by dx squared and the second derivative of g with respect to x squared, right? And no higher derivatives, right? And that follows from the fact that the original Poisson equation has second derivatives with respect to the coordinates, right? So first and second derivatives of the metric only, and then we are going to require that G mu nu is symmetric, right? So that means that G mu nu is equal to G nu mu, right? And that follows from the fact that we know that the T mu nu is symmetric, right? The energy momentum tensor that acts as a source for the gravitational field is a symmetric tensor, so that symmetry has to be reflected also in the G mu nu, which of course cuts down the number of components significantly, right? We know now that because of the symmetry, the G mu nu will have 10 independent components in 4 dimensions, right? So we also know that the energy momentum tensor is conserved. So we know that the T mu nu is conserved. Right? So that means that when you take T mu nu, semicolon nu, this is equal to 0. Right? The energy momentum tensor is locally conserved. Right? Each point in space-time, this derivative is 0. Right? And you do have to remember that this derivative is not entirely trivial because it is this covariant derivative. Right? So it is an ordinary derivative plus 2 terms that involve the affine connection. Right? And that is where the semicolon comes in. Right? And the fact that the T mu nu is covariantly conserved immediately implied that the same thing has to apply to the G mu nu, namely G mu nu semicolon nu has to be equal to 0. Okay, so that is an additional requirement. And the final requirement that we have, which I'm going to cram here at the bottom, is that in some suitable limit, we should get back Newtonian gravity. Right? So in the non-relativistic limit, right, we should get back the equation that Laplacian of phi, or we can write in terms of the G naught naught, right? And so, in fact, we can just simply write that the G naught naught is going to be proportional to the Laplacian of the little g naught naught, right? So if we look just at the naught components, then this has to reduce to Newton's equation. Now remember that the T naught naught is just rho, right? So now what is remarkable is that these requirements, I believe there's 5 of them, these requirements actually uniquely determine the form of the G mu nu. Uniquely determine the form of the G mu nu. So it is possible to follow each one of them, and at the end you end up with a set of field equations that are completely unambiguous, right? So the fact that the G mu nu is a tensor and it is made out of first and second derivatives of the metric tells us that the G mu nu, right, has to be equal to let's say C1 times R mu nu plus C2 times, well, we can construct a second object that has two indices and is symmetric, and it is going to be proportional to G mu nu, but it does have to have these derivatives, so it is G mu nu times this Ricci scalar or scalar curvature, right? So this follows from these two requirements, and that is all you can have, right? And so now what we do require as well is this third property. Sorry, this is satisfied as well because it's symmetric, right? So the remaining property, the next one, is that it should have a vanishing covariant divergence. In other words, we want to have that G mu nu semicolon mu, right, that this object here is equal to so this is equal to 1/2 of C1 plus C2 times R semicolon nu, and that is due to the Bianchi identity. This Bianchi identity discussed at the end of the last lecture, right? And so that implies, right? That implies that, what is it down here, that this has to be 0. Has to be 0. Now, of course, the other possibility is that the covariant derivative, which for a scalar is just the ordinary derivative, that would be 0, but that would be very restrictive. So there is no reason to expect that this quantity here be equal to 0. So the only way by which we can ensure that this property right here is satisfied is that actually the coefficients match up, right? So if the coefficients match up, then that simply tells us that the C2 is equal to -1/2 times the C1. C2 is -1/2 of the C1. And so that means that we are already down to just one single term, right? Namely that the G mu nu is equal to C1 times R mu nu minus 1/2 G mu nu R, right? So this is the combination that actually satisfies this Bianchi identity, and there is no other that does that. So what remains now is the determination of a single constant C1 and not two as we did before. So now the hard work starts, because the next step is to look at the last item we have on this list, which is the non-relativistic limit, right? So next look at the non-relativistic limit, right? So non-relativistic limit means that we are going to look at basically two sorts of approximation. The first one is that whatever particles are included in the T mu nu, they move slowly, right? So that means small velocities in the T mu nu. So that means that dx mu by d tau is, is small, right, for mu equal to 1, 2, and 3, right, for the spatial indices, right? And so that's one thing. And the other thing is that we require the field to be weak. The field to be weak. So that will have important implications in a moment, because you do remember that the Riemann tensor, and already in fact the affine connection, is nonlinear in the metric, right? The affine connection contains the inverse of the metric. And the Riemann tensor, right? So now we got to remember that the affine connection, right, is something like 1/2 times g to the minus 1 times derivatives of g plus derivative of g minus some other derivative of g, right? So the affine connection has a rather complicated structure in terms of metric, and if you assume that the metric is weak, then of course that will simplify already at this stage, because, right, so you're going to write the metric g mu nu as eta mu nu, which is the flat metric, plus some small correction, right? And so that's going to simplify the calculation, for example, of the inverse, right? It will make the expressions a lot simpler. And the same is true of the Riemann tensor, because if you remember, the Riemann tensor is now obtained, again in a schematic way, by taking the derivative of the affine connection minus some other derivatives of the affine connection, and then plus terms which are of the type gamma gamma, right? Terms that are of this type. Right? And so you see that there are lots of terms which are nonlinear, right? There is a nonlinearity in the Riemann tensor, which is coming from the fact that you have these terms which are quadratic in the affine connection, right? And so by taking the weak field limit, this simplifies tremendously, because, for example, in the limit in which the field is weak, the quadratic terms in the Riemann tensor, you can actually drop those and just look at the linear terms, right? So we're going to plunge into that, right? Plunge into that, and so we'll first look at the term that appears in the Ricci tensor, right? So we are going to have, first of all, we're going to assume, because the velocities are small, that the Tij components are going to be much less than the T naught naught components, right? And that has to do with this velocity business here, right? And so that means that when you write out the field equations, right? So the field equations are r mu nu minus 1/2 g mu nu times r, and then multiplied by this C1. And this is going to be minus 8 pi g times t mu nu, right? So if these components here are very small, then what you have on the right-hand side is essentially just a T naught naught. And what you're going to have for the naught naught components, what you're going to have on this side is the R naught naught and the G naught naught, right? So that in turn implies that, so the fact that this Tij is small implies that for the ij components, these two terms have to cancel out more or less, and that you have to have Rij be of the order of 1/2 Gij of the scalar curvature, right? Has to be a cancellation. It doesn't mean that they individually are zero, right? They don't have to be zero individually. This combination has to be small so that it's compatible with the fact that the Tij is also small, right? And so now we look at the scalar curvature, right? And so the scalar curvature is defined as g mu nu times r mu nu, right? And now remember that the metric is very close to flat, right? So g mu nu is very close to a flat metric, right? And the flat metric, of course, with our convention is minus 1, 1, 1, 1, and the rest is 0, right? So doing this kind of raising and lowering indices to leading order, right, is fairly easy, because you're just multiplying by a matrix which is a constant, right? So all this raising and lowering business is going to become very, very easy to do. And so when you write out, this is going to become the flat metric to leading order, right? And so you just have the RKK component, right, summed over k, and minus the R naught naught, right, with the relative minus sign coming from the fact that you have a minus 1 in the metric. And so this in turn is, well, this is just a 1/2 by the equations of motion, by the fact that this is 0, right? This is equal to 1/2 times 8ij or in this case with the two indices the same. So eta kk times r. And so eta kk is the sum over k of the spatial components, and that's these three here, 1, 1, 1. So the trace is equal to 3. So this is just equal to 3/2 times r. So this is equal to 3/2 times r minus r naught naught. So you have that the scalar curvature is equal to 3/2 times the scalar curvature minus the r naught naught. So from that you can solve for the r naught naught, right? And so this tells us that the r is approximately twice the r naught naught, right? So now we come to the object that enters the field equations itself, which is the g mu nu, or in our case, the g naught naught, right? So the g naught naught is made out of the r naught naught minus 1/2 the g naught naught times the r. But the r we just calculated, so that's equal to 2 times r naught naught. So the g naught naught is equal to this constant c1 that still needs to be determined, times the r naught naught minus 1/2, right, the eta naught naught, the flat matrix times r. But now we use the fact that the r is equal to 2 times the r naught naught. And so this is equal to 2 times c1 times the r naught naught. Okay, so we've brought down the initial complexity of the naught naught component of the field equation to just the r naught naught entry that we need to calculate, right? Now, so what is the r mu nu? Well, remember the r mu nu, the Ricci tensor is just a contraction of the Riemann tensor. So the r mu nu is equal to g lambda sigma of r lambda mu sigma nu, right? And so this is the flat metric again, right? So it's essentially 1, right, or minus 1. Right? So what we need to know are the components of this thing over here. And so what we need, now we finally have to look up what this Riemann tensor looks like, right? And so we need to look up our lambda. Let me get the indices in the same order that I have them here, our lambda, mu, nu, and kappa. And we only need the linear part, which involves second derivatives of metric, because the nonlinear part is of higher order in this expansion. And so the linear part is equal to, first of all, there is a 1/2 in front. And this 1/2 is coming from the definition of the affine connection. Remember that the gamma, right? The gamma was equal to 1/2 times g to the minus 1 times this thing. See, that's where this 1/2 is coming from. And so we write the terms in the Riemann tensor directly in terms of the metric now. And so in terms of the metric, there is a second derivative of g lambda nu, derivative with respect to xk x mu. That's one term, minus the second derivative of g mu nu with respect to xk and x lambda, and then minus the second derivative of g lambda k with respect to xk, x nu, and x mu, and then plus the second derivative, last term, these are the 4 terms that we'll need, the second derivative of g mu k, derivative with respect to x nu and x lambda, and plus the nonlinear terms, which we're not going to look at. Now, we need the r naught naught, so that means that the mu and nu here are 0, right? So this is 0 and this is 0. Right? So we need 2 indices which are 0. This one's 0 and that one is 0, right? And so we stare at this thing for a little bit, and we do remember we do remember that the Riemann tensor is antisymmetric in the first and the second pair of indices. It is antisymmetric in this pair, it is antisymmetric in that pair, right, by the very definition of it, which means that this index nu cannot be 0, and this index lambda cannot be 0. So that means that this will be, say, an I, and this will be a j, right? And so now we look at these various terms, and we see what kind of derivatives we get. So we know that mu and k are, we know that mu and k are 0, right? So we have a mu here, and we have a nu there, and we have a mu and a nu here. Mu and k, sorry, mu and k. Mu and k are 0. So we have a mu and k here. We have a mu and a k here. And we have a mu and a k here. And in the last case, we have the mu and the k appearing there. Now, I will argue that, in fact, the first three terms, we can forget about them, and all we need to keep is the last one, which is nice, only one term. And why is that? Because we are going to assume that the fields are weak and that they're essentially time independent, because we are going to get Poisson's equation, which is time independent. Now, the derivative with respect to xk, dxk or dx mu is going to be a derivative with respect to time, right? Time, because mu and k are not, right? Time. So dg by dt is going to be 0, right? And so that tells us that these terms we don't need to look at, right? And so we only have to be concerned about that last term, which is nice. Right? So we can go back to this side and come to the conclusion that, in fact, what we do need is the R naught naught. And we know what it looks like in terms of the metric. Right, so the R naught naught is 0, and the Ri naught j naught is this derivative term, right? So 1/2 times dg naught naught, second derivative. Right? It's this last term. Second derivative with respect to nu and lambda, right? Nu and lambda have to be spatial indices, so they have to be I and j. So it's dxi and dxj. And that's all we have, okay? So that leads us to conclude that the g naught naught, the capital G naught naught, which is up to a constant equal dr naught naught, where dr naught naught is just a contraction of Riemann, where this is essentially a unit matrix, so it doesn't do anything, is just this object here, which has only one leftover term, which is what we just wrote. So this is essentially equal to 2c1 times ri0 j0 minus the r naught 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 naught, which is 0, right? And so this is equal to 2c1. Now, sorry, the other thing is that these two indices are the same, right? Because we are doing a contraction. A contraction means that we're multiplying this by the flat metric, right? And the flat metric is essentially a Kronecker delta except for the -1, which means that the lambda and the sigma indices are going to be the same. So these two indices, the lambda and the sigma, the first and the third one have to be the same. So that means that I and j are the same index. And so when I and j are the same index, of course, what we get is just a Laplacian. Right, so what we get is just a Laplacian. So it's 2c1 times 1/2 times the gradient squared, or the Laplacian, of g naught naught. Right. And so the 1/2s cancel out, and so we get just c1 times the Laplacian of g naught naught. Right? And so now we compare this to the original equation. Now you do remember that g mu nu was minus 8 pi g times t mu nu, right? And so that leads us to the g naught naught being minus 8 pi g times the t naught naught, right? And well, the g naught naught, we just determined that. Right, the t naught naught, we just determined that. Right, the g naught naught is equal to c1 times the Laplacian of g naught naught. And we also know that the t naught naught is for you know, a system that we discussed, a non-relativistic system where the velocities are negligible, is just a rho. And so that finally gives us that c1 is equal to 1. c1 is equal to 1, right? And so we're done. We're done. So we see that, in fact, the requirement that we wrote down at the beginning, right, those 5 items that we had to satisfy, the fact it was a tensor, first and second derivatives of the metric, that would satisfy the Bianchi identity and that would give the correct non-relativistic limit, and it would be symmetric, right, for the g mu nu, that those uniquely determine the field equations, right? So we conclude that the correct field equations are r mu nu minus 1/2 g mu nu times r is equal to minus 8 pi g times t mu nu, right? That these are the correct field equations for relativistic gravity, right? And so this is what Einstein wrote down in 1916, right? So there's 1916 field equations. And so now we can stare at this expression a little bit and think of what you know, we have achieved and how we can look at this. It is clear that this t mu nu has to do with matter in all its forms, right? So it could be non-relativistic matter, like dirt, you know, or stars. It could be relativistic matter, so that would be like neutrinos, for example. It could be also photons, right? So if you have particles that propagate at the speed of light, which are non-gravitational, right, then they're all lumped in here, right? So the t mu nu is what represents the energy and momentum of all matter components in the universe, including, of course, also dark matter, for example, right? And this part here is the gravity part. The gravity part, right? The gravitational field is located on the left-hand side, and that is what contains all the metric in it, and it is, of course, highly nonlinear, right? This equation is nonlinear. Nonlinear. That was kind of expected, right? We can make, at this stage, perhaps again a comparison with the equations for electromagnetism, right? In electromagnetism, Maxwell's equations are linear, right? And that is a reflection of the fact that when you have a photon, right, a photon will interact with an electromagnetic current, will interact with an electron, but the photon carries no charge and it does not interact with itself, right? So the reason for why the Maxwell's equations are linear is that the photon is not charged, right? That, of course, changes a little bit in non-abelian gauge theories, where the gauge bosons, in fact, do carry a charge. But in electromagnetism, photons will just go by each other, right? They will not interact. They will interact with currents. Here, this is dramatically different. It's dramatically different because the analog of the charge in gravity, of course, is the energy momentum of the field. And anything carries energy and momentum, right? Including the gravitational field. So if you have a lump of a gravitational field, that will have energy and momentum associated with it, right? Because of the fact that it exists somewhere. And it will self-interact. So this self-interaction is something that you cannot take out of gravity. It's part of the nature of gravity, that it has to be nonlinear, right? And of course, in a quantum description, it says that the graviton will, of course, interact with itself. If you have a graviton that's propagating through empty space, it does carry energy and momentum, and it will interact nonlinearly with itself. And that is, of course, one of the reasons, right? One of the reasons while general relativity, and in particular the relativistic field equations, are so difficult, right? They're so difficult to treat. Already at the classical level, right, we do appreciate very early on in our career how fairly easy it is to solve a linear differential equation, right? We're actually quite lucky that even when we do quantum mechanics, we only have to solve, as far as the Schrödinger equation is concerned, just a linear partial differential equation. And so the methods to do that are well known, and usually you can get a solution pretty quickly by using, say, Frobenius methods or whatever methods that we develop in the context of quantum mechanics in terms of known special functions and so forth. The big headache here is that the equations are fundamentally nonlinear, and because they're nonlinear, they're very hard to solve. That is, you have to guess a certain form of the metric and then plug it into the equation and see whether you can satisfy it or not. So that is why, for example, the static isotropic solution for a gravitational field was discovered very early on by Schwarzschild in 1916. And so that would describe something like a black hole. And it took another 50 years or so to actually find a solution for a rotating black hole, which is the Kerr solution. So we shall see at some point, perhaps, how complicated it is to actually just find this relatively simple, in relative terms at least, solution to a rotating object in general relativity. Because of the nonlinearity of the field equations, even if you assume that the metric has a fairly simple form to start with, by the time you calculate all these derivatives of the affine connection and the Riemann tensor and so forth, you end up with some horrible description. And it is even less surprising that by the time you get to the quantum theory, because of these nonlinearities, the problem becomes very tricky. And approximations such as doing some sort of expansion for weak fields don't lead anywhere, because gravity is not very easily treated by using a weak field expansion where you assume that the field is weak. In general, the field is not weak, and that is certainly true, in my opinion, in the quantum context, where you allow for fluctuations of the fields, and the fluctuations generally are not small. There's no way to constrain the fluctuation to be small. So gravity has been a big headache, and for a long time, both at the classical level, where a lot of it is nowadays under control, but even more so at the level of the quantum theory. Nevertheless, it is an amazing theory, right? Because we recognize that, in a sense, what can we say? We can say that Einstein was very lucky. Why was Einstein very lucky? He was very lucky because in 1916, right, what people had known and discovered at the level of differential geometry was that in 4 dimensions, when you describe a curved manifold, it was described in terms of a Riemann tensor, right? But he was very lucky because it turned out that when you tried to write down terms that only had first and second derivatives, you could only construct 2 things, right? The r mu nu and the g mu nu times the r, right? Well, that of course could have still be a problem, right? Because you had 2 terms, but you only had one non-relativistic limit, which was this Poisson equation, right? Which had the phi in it and had the Newton's constant. So you might have had 2 coefficients that you needed to determine. But there was this Bianchi identity, right? And the Bianchi identity actually says that you can only have a certain combination, right? The Bianchi identity tells you that you can't have the r mu nu by itself. You can't have the second term by itself. You have to have this difference between the 2. And if you have that difference, then the divergence of that is 0. And that uniquely, that factor of 1/2 is crucial, right? So the Bianchi identity was a crucial ingredient. Now, it actually turns out that Einstein did not know about the Bianchi identity initially, right? When he was fiddling around with his equations in 1916, the first equation that he wrote down was this. He wrote down this equation because he said, what can I construct out of the Riemann tensor that has only 2 indices, right, and which is symmetric? Well, it's the r mu nu. That's the object that naturally comes to mind, right? And so his first attempt at the field equations was this, and he did a number of calculations. And then somebody said, there is this identity There is this identity, and that identity says that if you take the covariant divergence of this is not 0. But this is 0 when you do the covariant divergence. And so your equation, if you write it in that form, is inconsistent. It violates local energy and momentum conservation. And so Einstein said, oh yeah, of course, I need to take the Bianchi identity into account. And when that happened, then of course the -1/2 g mu nu was added on, and that fixed the issue, okay? But nevertheless, I mean, in spite of, the presentation that I've done here, which seems to be rather simple and streamlined in many ways, he was lucky because it turned out that out of the Riemann tensor, you can only construct two objects that have two indices, mu and nu, and one is the Ricci one, the Ricci tensor, and the other one is g mu nu times r, and that's the end of it. Because if you had a third one, then you would be in trouble, right? If you had a third one, then you wouldn't know how to constrain the coefficient of the third term, right? And so I'm sure, at the time when he discovered this, he probably fell off his chair because he was very pleasantly surprised, and pleasantly surprised by the fact that you can construct a relativistic theory of gravity just on invariant principle, just based on the principle of general covariance, and the fact it has to be written out in tensors, and you don't need anything else. You just need to know what Newton's equation looked like, what the Poisson equation looked like. And so that was amazing. That's amazing. So there's nothing to adjust here. This new theory that you write down doesn't have to be now fitted to experimental data to determine some set of coefficients and to see what they would be. Everything is fixed. Everything is fixed. Because the quantity that appears in here is the old 16th century Newton's constant, right? And the T mu nu, of course, you know what exactly that looks like because we discussed it, right? If you have n particles, you can write it down. If you have a perfect fluid, you can write it down. And what appears on the left-hand side, also, we know how to write that down. So everything is determined. So it is, of course, an astonishing equation, right? It is even more so astonishing given the fact that the field now does not have a single component, like the g naught naught or the phi, but now there are 10 fields. There are 10 fields, which means there are all sorts of new effects, right? And all those new effects are completely determined by this equation. So now you have to sit down, get a piece of paper, right, and a number of pencils, and you can start trying to find solutions to these equations. And it's just a matter of working out what the predictions are, because it is now very similar as what happens in the case of Maxwell's equation, right? In Maxwell's equation, we go through Jackson and start out with static solutions, and then we do magnetostatics and move up to time-dependent solutions, right? So here you have the same situation. The equations are given, and you can now look at different contexts to see what kind of solutions you will obtain. Now, there's more than one way of writing these equations, because you can, in fact, move this term over on that side. So let me give you an equivalent form, right? Equivalent form, right? So equivalent form is one where you take, first of all, the trace, right? So taking the trace means that you just multiply this equation by g mu nu, right? So you take this multiply by the matrix G and then take the first and last indices to be the same. So it is essentially a sort of a trace, right? And so for the first term, you get the g mu nu times r mu nu, which is just the Ricci scalar. So from the second term, you get -1/2, right? And so -1/2 times, well, the trace of the g mu nu, because it's like an identity matrix, except it has a minus sign, but the trace done the proper way with the g mu nu gives you 4. So that is the trace of the g mu nu, and then you get times r again, because that's what appears there. And so this is equal to -8 pi g times the trace of t, right? So the trace of t, we can write it like this, or we can write it like that. It's the same thing, right? So you're going to write it like this, like that. And so we have that R is equal to 8 pi g times the trace of the energy momentum tensor. Right, so the scalar curvature is, if you wish, determined by the trace of the energy momentum tensor, but that allows us to actually go into the original field equation and replace this, right? If you want, right, you can replace this by R is equal to 8 pi g times the trace of the energy momentum tensor. And so when you do that, then in this form, of course, one would think that it's better to bring it over on the right-hand side, right? Because it looks like it's a contribution from the matter fields, right? And so an equivalent form is that R mu nu is equal to minus 8 pi g, right? And now we have an expression in parentheses, which is T mu nu minus 1/2 g mu nu times the trace of the energy momentum tensor. We can write as T, or we can just make the trace explicitly and write it in this form. Okay, so this is an equivalent form of the field equations. And so we can stare at this as well, and we can conclude that in this equation, we just have the Ricci tensor, and that the source for the Ricci tensor is actually not the T mu nu, right? If you really want to force it, the field equations in this way, then the source would be the T mu nu minus the trace part, right? The two equations are completely equivalent, and we would describe this again as the matter part, right? Matter part. But of course we have to be very careful when we talk about a matter part versus a pure gravity part, because you notice that in here the gravitational field appears, right? So whenever you write down a T mu nu, there's likely to be hidden somewhere also the metric. So the gravitational field tends to appear everywhere, right? Because you have to make sure, after all, that these objects are genuine tensors, right? And that cannot be achieved unless you have, in fact, the metric that does these things for you, right? So in particular, though, we conclude that if we are, I can actually write it out here, we conclude that if you are in a vacuum, right, if you are in a vacuum, so a vacuum means that you have empty space and that there is no matter distribution in that region, right? So the T mu nu vanishes in that region, then you have to have that R mu nu is equal to 0. Right, so the solutions to Einstein's equation in a vacuum are that R mu nu is equal to 0, right? And so that again is similar to what you have in electromagnetism when you are away from any sort of sources, right? So you're looking at empty space, and of course in empty space it doesn't have to be empty, right? Because in empty space what you can have is the propagation of a photon, right? So away from any sort of distribution of charges in a vacuum, you still have the propagation of electromagnetic fields. You have propagation of photons in a quantum mechanical language. And that is going to be true here as well. This is going to be the equation for gravitational fields, right, that are describing gravitational waves. So gravitational waves obey this kind of equation. Of course, any sort of field in a vacuum obeys that equation, but that includes gravitational waves. And so the fact that R mu nu is 0 does not imply, right, one has to understand that this does not imply that R mu nu lambda sigma is equal to 0, right? So one has to understand that the field equations in a vacuum tells us that the Ricci tensor has to vanish, but the Ricci tensor is not all there is to about gravitational fields and curved space and so forth, because the fundamental object is actually the Riemann tensor. And you remember that this is related to that by essentially taking some sort of trace, right? Because you are taking some of these indices to be equal and then contracting with the metric, right? And so you do understand, of course, that if something has a vanishing trace, that doesn't mean that the matrix elements themselves are 0, right? So they could adjust so that the trace is 0. So this is a little bit of kind of a trace equation, right? It tells us that the fact that Ricci is 0 does not imply that the Riemann tensor is 0. So one can in fact verify that for example, for a static solution of the field equation, like the Schwarzschild solution, you in fact have that this is identically 0, but this one is not, right? So, so the fact that the Ricci tensor is 0, in other words, does not say that there is no gravitational field. You can have a gravitational field even though the R mu nu is 0. The constraint of the field equation is that R mu nu is 0, but that does not imply that you can have a traveling wave somewhere. Well, there is a little bit of a flaw in this argument, because what we have in fact discussed so far is what kind of field equation you get if you assume that those 5 points, which I wrote at the beginning of the lecture, are satisfied. Right, so there's a small flaw. In the argument or the arguments, right? Because, well, let's remember again, we did require that G mu nu was a tensor, that the whole equation was written in terms of tensor. We did require that whatever tensor it appeared in the field equation contained first and second derivatives of a metric, that it was symmetric, that the Bianchi identity would be satisfied, and that the correct non-relativistic limit would be recovered. Well, the problem is with point number 2. Because point number 2 stated that the G mu nu, right, has to contain first derivatives of the metric and second derivatives of the metric, right? In fact, these usually end up being squared, right? Well, that is something that you can relax. You can relax. That is, you can say, well, look, maybe I should include something that doesn't have any derivatives. Is that possible? And the answer is yes, because if you look at the field equations, then you have R mu nu minus a half G mu nu times R. And obviously, something that you can add is the metric itself. So it is a term that is of this type. It is a term that is of this type. So, and I'm following here the Weinberg convention, right? The metric that we use here. And the convention for the Riemann tensor is such that when you add this constant, it gets added with a minus sign. Basically because the convention we're using in this course is that Riemann is defined in such a way that it quite often ends up, if you look at spatial manifolds, it ends up being a negative quantity. And so when you add the G mu nu term, you want to add that also with a minus sign. So I think in some books you'll find the plus sign. We're all talking about the same term, but the difference in sign just has to do with the fact that there's different conventions for Riemann. And so that is the infamous cosmological constant term. Cosmological constant term. So that is a new term that is possible in the field equations. And so all the things that we said up to this point, right, that the field equations are unique, well, it is true if you just assume that you have in the G derivatives of the metric, but if you allow for a term that does not contain any derivatives, which is in fact a very simple term, then this will satisfy all the other requirements, right? It will satisfy the requirement that this is a tensor equation. It involves an object which is constructed, of course, out of the metric and is symmetric, right? And does it satisfy the Bianchi identity? We might worry about that. That is satisfy the Bianchi identity. The Bianchi identity states that when you take the covariant divergence on the left and right hand side, they're both 0, right? And so what about the covariant divergence of this thing? Well, this actually satisfies. This was one of the issues that we had in trying to construct derivatives of the metric, is that they would always end up 0, because in fact we know that G mu nu semicolon lambda is always 0. right? There's this divergence is always, this derivative, sorry, is always 0. And so when you take a divergence, of course, it's 0 too, because you just do a contraction after you take the divergence. And so you can add that term. It's perfectly legitimate. And now the history of this development is somewhat contorted, right? Because Einstein presumably realized early on that you could have a term like that. But, well, it didn't seem to be necessary. And nobody had heard about anything like this before, and so he just left it out. And so his equations, of course, once he started to work out simple solutions, in particular what happened when you have a homogeneous isotropic distribution of matter, he found that his universes had a tendency to expand, right? And this was about 1919, 1920. So his model predicted that for a suitable mass distribution given, say, by this perfect fluid form, right, that you would have to, you'd find that this mass distribution would either tend to expand or contract, and you would not have a stable solution, right, unless you fine-tuned a few things. And so he was disturbed by that, and everybody told him, you know, the universe is, look out the window, it's not expanding, we know that, right? So in order to find something that was actually static, he introduced this lambda term, right? Because the lambda term does affect the cosmological evolution significantly. And that was in 1922 that he actually discussed this lambda term explicitly. And then soon after that, 1924 all the way to 1929, Edwin Hubble here at the Mount Wilson Observatory above Pasadena discovered actually the universe is expanding, right? So in fact, the Einstein equations were in beautiful agreement, right, with Hubble's observations, provided you didn't have this lambda, right? And so Einstein was somewhat embarrassed by this, right? And he referred to the lambda term as the biggest mistake he had done in his life, because he introduced a term to fix what he perceived to be a problem. And of course, that problem was not there in the end, and that term was not needed. So it was a big nuisance, right? It was a big nuisance. But it is interesting that it is a relativistic term. It is a relativistic term. It's something that comes in. And while Einstein was disturbed by it, Einstein, of course, was disturbed by a number of things we know. He was disturbed by quantum mechanics as well, right? God does not play dice, so it didn't like some aspects of quantum mechanics either. But certainly was disturbed by this one. And but 50 years later, of course, there was a long debate on whether lambda is 0 or not. If I talked to any of my colleagues that were working on supersymmetry, they would tell me that lambda is 0, of course, because everything cancels and the vacuum energy is 0. But in 1999, observations were done on distant supernova, and the people that did these observations, most of them based actually at Berkeley, they found out that there is a lambda term. There's a lambda term. It's small. It's small, so you don't see it right away. Of course, you don't see it in laboratory experiments. It does modify gravity. Does it modify gravity? How would you know if it modifies gravity? Can we see that it modifies gravity? Well, what is gravity on laboratory scales? When you go to the basement and play around with the torsion balance, all we need is what equation? Poisson's equation, right, essentially, right? Because this is kind of a relativistic modification of it, but if relativistic effects are not important, then Poisson's equation is pretty good. This does not modify Poisson equation at all, does it? Yes, it does. Of course it does. You can see that immediately. Well, let's look again like we did for look at the naught-naught equation, right? So we have R naught-naught minus a half G naught-naught R minus lambda G naught-naught. Lambda G naught-naught is 0. No, of course it's not, right? Because the G naught-naught is equal to minus 1 plus 2 phi. Okay, so we get a lambda G naught-naught term, which is like this. And so we have lambda times phi. So this modifies Newton's equation. If you want, it modifies the Poisson equation. There is an extra term in the Poisson equation. Poisson, right? And so it's actually not entirely straightforward to sort this out, of what happens exactly when you have a lambda term. And in fact, some of the arguments I will give are not actually good arguments, but you have to work a little bit more to actually sort out correctly what happens. But you can do the weak field limit again, right? So assume that all the fields are weak, expand everything out, and assume that you have non-relativistic method which moves slowly, right? And then you find out in that limit that the Poisson equation becomes, let me write it over on this blackboard because it's need a little bit more space. Poisson equation is modified too. There's extra terms. So first of all, of course, we have the Laplacian term. That's not going to go away, right? And we also have the source term, which is 4 pi times rho, right? But we have a new term, which is lambda times phi. And this is equal to lambda over 2 minus 4 pi g times rho, right? And well, we're going to put an approximate sign here because, of course, this is based on the weak field expansion, and also it assumes that lambda is small. I think that makes the calculation a little bit easier to do. And so there are two new effects. And you should do this, by the way, as an exercise. I think it's nice to work out this limit when you have the lambda. And so there are two new effects. The first effect is that the Laplacian contribution gets an extra piece attached to it. And that piece, of course, whoever is taking, the quantum mechanics class right now with me or is taking quantum field theory recognizes that that term, this term here, what does it look like? As a mass term, right? So this is a mass term. It's a mass-like term. Right? So all of a sudden, it looks like the field has acquired a mass, right? And so that is something, of course, we need to be very concerned about because in ordinary gravity, lambda is 0. And the photon is massless, and you have very long-range forces. So if the field, for some reason, if this argument was in fact correct, it is not quite correct, but if this argument was correct, then the field would acquire a mass, and you would get some sort of Yukawa potential, right? The solutions would be Yukawa-like, right? Namely that phi of r for a point distribution, for a point source, would be e to the minus the square of lambda times r divided by r, right, times some constant in front, right? You would have a Yukawa type potential, which means the gravitational field would have a finite range. So that would be the first concern. The other thing is that if we look at this side here, we have, of course, the mass density distribution, right? So you think of a universe where you have all sorts of masses lying around, and there is a rho which describes that distribution. But here we have another term which is in fact constant. So it is a uniform mass or energy distribution. Right? Mass and energy are the same. So it looks like all of a sudden this Poisson equation, besides that mass-like term, also has some source term. There's a source term, right? And that source term is some sort of energy distribution which is there everywhere. And of course is constant. It's constant because lambda is a number, right? Can lambda be a lambda of x? Can you have a lambda of x so that this cosmological constant depends on where you're at? That, of course, would be problematic because you would run again into problems of general covariance. So you cannot have something like this. So lambda is strictly a constant, right? Even though there are scalar tensors theories where you can have scalar field contribution. But here it's a constant. So it's a uniform mass energy density distribution which is constant throughout the whole universe. And well, that is puzzling, of course. It's puzzling if you think of it from the classical point of view, Quantum mechanically, it would look like a vacuum energy. Quantum mechanically, we're less puzzled. We're less puzzled by energy or mass distributions which are uniform, because we do encounter this vacuum energy very early on when we describe quantum fields, for example, right? Remember that if you just have the electromagnetic field, there is a vacuum energy, which is the zero-point energy of all the harmonic oscillators that describe an electromagnetic field, right? So it's 1/2 h bar omega for each degree of freedom, and that's, of course, an infinite quantity when you integrate over all frequencies, over all omegas. So in quantum mechanics, we're not that surprised that the vacuum has an energy. It can happen. Classically, I would say no, right? We can't really visualize that. Well, nowadays, as I said, the cosmological constant has been found to be non-zero, and so this is called dark energy. But when somebody talks about the cosmological constant, the vacuum energy, the dark energy, they're usually talking about the same thing. It's the same thing, right? Physicists are very good at inventing new names for things, but we're most of the time, what is referred today as dark energy is in fact the cosmological constant, right? Now there are, of course, diehards which believe that this dark energy is something else, that it's not the cosmological constant. And of course that could be. That could very well be that this dark energy, because astronomers, that do the observations, they don't want to commit themselves to any specific model. They just say, well, if I look at these distant supernovas, it looks like there is a term that I have to include that has this and this properties, and that could be a cosmological constant, or it could be something else, or a combination of the two, and that is, of course, possible. So astronomers and astrophysicists usually refer to this as dark energy. Somebody that, like me, has been teaching relativity, of course, for a number of years, general relativists immediately recognize this as the cosmological constant term as being the most likely explanation of what is going on, right? Why would it be for such a term to be naturally present? Well, because Einstein's theory, which we know is based on some rather fundamental and compelling principles, tells us that something like this is possible. Right? Einstein's equation says that there is really no reason not to include a term like this, that a term like this is consistent with everything that we have said since the beginning of this class, general covariance, energy momentum conservation, and so forth. So it's not excluded by any good argument, and so presumably nature makes use of it, right? When something is not excluded, then one should look for it, because there's a good chance that it does appear. And if it doesn't appear, then one should really think of what the reason for that would be, because that's kind of mysterious that it's not there. So it's there, it's observed, and the cosmological constant is a natural candidate to explain this dark energy. Now, you can construct, right? If you compare this to this, right, you can force this term to look like a rho type of thing, because you can multiply and divide by g, right? So there is, in fact, a rho lambda, right, which is lambda divided by 8 pi g, right? So you can define, if you want, if you really insist, you can define an energy density, a rho, which is associated with the cosmological constant, right? And that has that value, right? And if you work out what that number is, it's about 10 to the minus 4 electron volts to the fourth power, something like that. It's a very tiny quantity. Now, in more perhaps useful units, right? So lambda is some sort of vacuum energy, right? Vacuum energy, we can see it from that equation, or we can even see it from here, right? Because you can, in fact, take this lambda g mu nu term and you can bring it over on this side, right? So it acts like some piece of a t mu nu, right? And it is also, it can be described as as some sort of curvature of empty space. It's a curvature of empty space because when you look at the field equations, right, this they acquire a non-zero curvature even when T mu nu is 0, right? If T mu nu is 0, then this part here is 0. And when you take the trace, this gives R. This gives minus a half times 4 times R. And the trace of G mu nu is again 4, right? So you get R is equal to minus 4 lambda, right? So if there are no matter sources, then the scalar curvature is minus 4 lambda. So if lambda is 0, of course, the scalar curvature is 0 throughout empty space. But if lambda is non-zero, then there is some sort of intrinsic curvature everywhere, which is constant, right? Because this lambda is a constant number. So it can be described, the lambda can be described as a curvature of empty space, right? And from this relationship, or the original one, you can see that lambda has dimensions, right? Lambda has dimensions of 1 over length squared, right? Because a curvature always has dimension of 1 over length squared, right? And so you can now look at what the observational data tells us, right? The 1999 distant supernova survey, which has since been redone many times, and you find that this is of the order of 10 to the 28 centimeters squared, right? So it is, in fact, lambda is a very small number. The length scale that appears in it is huge. And in fact, this is comparable to the size of the universe. To the size of the visible universe. Now, the size of the visible universe is something that is usually associated with the Hubble constant, so it's associated with h naught to the minus 1. So, in fact, this is sometimes referred as some sort of a interesting coincidence, right? That the size of the visible universe today, which relates to the age of the universe, which we know is about, something like 13.8 billion years. That length scale or time scale seems to be of the same order as the lambda, right? The kind of length scales that come in are comparable. And so that is a little bit of a mystery, if you wish, and because they are, after all, at least from the beginning, it seems like they're quite different scales. In particular, the age of the universe, of course, gets bigger as we wait longer, whereas this lambda is kind of a constant quantity, at least in general relativity. It is just a number. So anyhow, it has that value. So because it is so small, right, because it is so small, it means that, of course, it has no observable effects whatsoever on laboratory scales. Right? If you do an experiment in the basement with a torsion balance, you're never going to see anything that is associated with such a gigantic scale. Right? So there is no modification of Newtonian gravity on laboratory scales. There's no modification of Newtonian gravity on solar system scales either. Right? Because here we're talking about the size of the whole universe. So the solar system size, of course, tiny, right? And even if you look at the galaxy itself, the Milky Way or certain nearby galaxies, the effects are also very small because this length scale is so huge. So the lambda, interestingly enough, seems to be there, but it is a tiny contribution, right? Nevertheless, tiny always means in relative terms. And by the way, you can also construct this invariant combination. If you look at lambda times g squared, this is of the order of 10 to the minus 120. You can construct a dimensionless number that is a combination of Newton's constant, which you remember has units when h bar c is equal to 1 as units of length squared. Right? So, actually, sorry, it's lambda times g. That combination is a tiny little number. And now, whether it is in the end ultimately very small or not, also has to do with at what scales you're looking at, because cosmological observations, which look at the larger scale, have come to the conclusion that most of the energy in the universe is dark energy, right? You might have heard this fact that dark energy accounts for about 75% of the known energy distribution in the universe. And so if that is a lambda term, then the lambda term would be 75% of that. And about 24%, the remaining 25%, 24% of that is dark matter. So there's a lot of dark matter out there, which we don't know what exactly it is, right? And then the stuff that makes us is about 1% or maybe less, right? So the actual baryons and the helium and hydrogen and flesh and so forth, stars, is only a small fraction of what seems to be out there. So the cosmological constant on cosmological scales gives a very important contribution, maybe 75% of the energy content of the universe. And so I think this is a good place to stop. And so unless there are any questions or comments, I think we should, yes?
Can you make lambda space-time dependent if you make the process derivatives to be 0?
Well, you have to, if you want to have lambda that depends on x, right? First of all, lambda that depends on t would be problematic, right? I mean, you could think that lambda is some sort of, effective vacuum energy, but that it changes during the evolution of the universe. That it was maybe small at the beginning and now it's bigger, or vice versa. Of course, as soon as you write down a lambda of t in the field equations, that violates general covariance. In fact, it violates Lorentz invariance, right? Because Lorentz invariance says that things should depend on t and x in a kind of symmetric way, and that you should have a Lorentz invariant formulation. So this obviously does not work, right? So you can have lambda of x, right? And so that would be a field. So that would be a scalar tensor theory. So you can think that the lambda would be due to some new field. Now the new field, we don't going to call that phi of x, because I think we tend to reserve phi of x for the Newtonian potential. So there would be some new field psi of x, right, which would be some sort of a scalar, right? And that psi of x would eventually give rise to a lambda of x in some suitable form, right? And well, if there is a scalar field psi of x, that scalar field has to be coupled to gravity in a covariant way, first of all. And presumably it also has derivative terms, right? So you want to have kinetic terms as well, right? So if such a field exists, then there will be kinetic terms as well. And of course, one attempt to extend gravity by adding a scalar field that to some extent will mimic also the existence of a cosmological constant, that is the Brans-Dicke theory, which we're going to discuss, I think, not in the next lecture, but the one after that. So there are scalar tensor extensions of gravity where you add a scalar field, and to some extent that can also mimic a cosmological constant. But of course, scalar fields, well, there are no fundamental scalar fields, are there? So, yeah, so scalar fields are problematic. I mean, we don't know of any fundamental scalar fields in our repertoire of particles except the Higgs, except possibly the Higgs. Of course, the Higgs was just discovered, right, recently, last summer, the announcement was made. And we don't know whether the Higgs is actually elementary or composite, right? And so there is this old Wilson argument that says the scalar fields are undesirable from a quantum field theory point of view because they tend to acquire masses due to quadratic mass divergences that make them very heavy. So unless you have some sort of miraculous cancellation in Feynman diagrams, then usually scalar fields are not liked. So scalar fields have been undesirable for a long time, but who knows? They might come in at some point. So we have lots of scalar fields, of course, around which are composite. The pion, for example, is an example of a scalar field, but that's not an elementary particle. So anyhow, there's all sorts of aspects of cosmology and general relativity which can be a little bit speculative, but what we are discussing in this class is what is established understanding. And the remarkable thing is that The relativistic theory of gravity has a set of equations which I can write down, which is uniquely determined if you allow just for first and second derivatives metric plus the lambda term, right? And so that says that, we should take it seriously because it's just like Maxwell's equation, right? It's a kind of unique equation. And in fact, one can go a step further and say that the quantum theory of gravity is uniquely determined by that as well, because the quantum theory of gravity takes that equation as the fundamental equation and works from there. So there are no adjustable parameters, right? No adjustable parameters of any sort in the classical theory or in the quantum theory at that stage, right? Which is like QED, of course. The reason why QED progressed very rapidly at some point in the 40s and 50s is because it was based on Maxwell's equations, which are unique. There's only one theory you can write down for a massless photon. That's Maxwell's equation. And the quantum electrodynamics just builds on that there's only one equation. So you know exactly what equation you're talking about. You don't have to add 137 parameters to get this quantum theory to work right. It's uniquely determined. So I believe, and some other people believe, that that's going to be true also for gravitation. That the symmetries, the general covariance, and constrains the theory completely has to be a quantum form of Einstein's theory, in my opinion, if it exists. Of course, it doesn't exist, then we have to think harder. But it's a tough problem because of nonlinearity. Anyhow, any other questions? All right, very good. So I'll see you on Thursday.